Hello, welcome everyone. I'm just going to make sure I can see the chat and see you all here. Hope we're all doing well. Welcome to today. We're going to be doing a mechanics topic today. So feel free to say hi in the chat. It'd be good to see your comments and see who's joined us today. I hope you're having a good weekend. We've got a really good topic in store. So we're going to do mechanics. We're going to look at SUVAT. Welcome. Hi, lovely to see you with people in the chat already. Ready to get started. So we're going to get cracking shortly. Please do feel free to ask any questions throughout and obviously share answers. It'd be really good to see who's done this topic before, how confident we are with it. So we're looking at SUVAT, which is a part of kinematics. Welcome. Hello. Excellent. Right. And I'm ready to get started now. So I'm going to share my slides with you and we'll get started working through the content. Please do, as I said, say hello in the chat, answer any questions and also share answers. That would be great. And questions as we go. Right, here we go. So let's get started. Should hopefully be able to see that. So we're going to look at SUVAT today, and it would be great to hear from you in the chat if this is a topic you've seen before, if you're quite familiar with SUVAT, to give me an idea of this, if this is revision or if this is really new content. But welcome, it's great to see so many of you here. And yeah, we're going to have a little look. Yes, I'll talk about how to answer the exam questions, particularly with rounding and the questions that involve gravity. That is particularly a kind of important bit. Excellent, right. So for some people, this is very much revision. Cool, lovely. And it is obviously in physics. There is that overlap with physics with this part of mechanics. Brilliant. Right, let's get started. So I'm Max, I'm head of maths at Snap Revise, and I did a maths degree not too long ago. And pretty much since then, I've been teaching maths at A level and below, so GCSE and Key Stage 3 as well. And mechanics is one of these big parts of the A level that really sort of shows off how much breadth there is to the maths A level and how you have to kind of understand so many different ideas to a really high standard. Oh, okay, interesting to hear that. So people, obviously, the course is divided up differently in different schools and colleges, obviously. So that's good to know. Excellent. Yes. Good, excellent. I can see some of the comments coming in. So depending on the exam board, depends on how we treat gravity. And obviously in physics, you might give it to more significant figures. But yeah, there is obviously that overlap. I will talk quickly about Snap Revise, and then at the end, I'm going to talk about some of the tutoring services that are on offer and a bit of a code for you to use. But just a quick reminder, so there's 4 classes a week for Maths A level, a year 12, a year 13 class, and 2 drop-ins where you can ask for support on any topics you have for homework that you're covering in school, or obviously if you have a test coming up. So it's really sort of tailor-made tuition that guides you through the whole A-level content. Excellent. Cool. And some people have seen this topic way before, which is great. So I'm keen to get onto that. We have this code today. I'll show you where to input this on the website later. There's a free trial for the Snap Revise platform and the tuition service that's available. So you can see the kind of backlog of different videos and classes we've done, if there's a specific focus you'd like to go back over. So I'll talk about that towards the end. I'm keen to get cracking with this, this topic. It does, as I said, overlap a bit with physics, but we're going to look at it in light of how it will appear in the A-level maths. Hopefully a useful reminder if you've seen it before. So we're going to look at the terms of the SUVAT equations, derive what the SUVAT equations actually are, and then actually use them to solve kinematics problems. We're not going to do the real extension of this that we see later in year 13, so projectiles and the differentiation part of kinematics, but we are going to look at and focus on SUVAT. Brilliant. So what we're going to start with, some kind of key ideas that really help us out, some key definitions. So displacement, does anyone know how we would define that? And then we're going to talk about it in light of the graph as well. So displacement, what do we understand by displacement? Good, so let's have a little think. Displacement is effectively, a lot of people think, oh, isn't it just the same as distance? And it kind of is. It's distance from a point in a given direction. So it's what we would call a vector quantity. Whoops. From a point in a given direction. Excellent, and thank you to those Lovely that are sharing answers in the chat. That's great. Distance from a point in a given direction. That is great. And obviously this, we're going to look at how to denote this and how we use this in SUVAT. We actually give it the symbol in SUVAT of S, which I think when people first see that, they're kind of a bit confused, like why is it S? But we'll go through and we'll get used to using that. And we use meters as the unit for measuring that. Velocity, for those that maybe haven't seen this sort of defined before, this is what we would call the rate of change of displacement. Okay, and it's good to think of it that way. Some people say, well, isn't it like the similar sort of version for speed, which effectively it is. It's like speed in a given direction, but it's good if we think about it as a rate of change of displacement, because that ties in with the idea of the graphs, gradients, eventually differentiation as well, and calculus. So understanding it as a rate of change, displacement per time. So that is the velocity, which we can denote with a V, and that will be measured in meters per second. Generally. Good, excellent, lovely. So hopefully we're going to clear up some ideas today and really build this up from scratch. So if this is something you've struggled with in the past, please don't worry and do feel free to ask the questions as we go. Rate of change of velocity. And it's sort of touched upon at GCSE in terms of velocity time graphs and stuff, but we're going to go over that. So this acceleration we measure in meters per second. So how much is the velocity itself changing per second? Newton's second law, does anyone know that one? Excellent, brilliant, thank you. Excellent in the chat there, that was very quick. Newton's second law is F equals to mass times acceleration, F being the resultant force. So this is often linked into some of the questions, and very well done to anyone that shared that. Lovely, well done. So resultant force. So the net effect of all the forces that are going on is equal to the mass times the acceleration. Brilliant. So this is mass, and we have to be kind of careful with this in the questions. And this is acceleration. Brilliant. Lovely. Right. The next bit, just in light of the graph that we've got here, there's a few key features of this that we need to kind of recognize if we're presented with a velocity time graph. So in terms of the gradient, which we may know as a rate of change, gradient is the rate of change of the velocity with respect to time. So actually the gradient on this graph is representative of acceleration. Okay. Acceleration. The area under it equals to the displacement. Whoops. And also, if we have a horizontal part of the graph, that represents that there's no acceleration, so constant velocity. Oh, sorry about that, guys. So constant velocity. Cool, brilliant. Right, very well done. Some brilliant comments in there. That's great to see. We're going to crack on. So this idea, this kinematics idea of SUVAT comes up in all the different exam boards. So it's a really key part of all the mechanics you're going to do. So what we're going to do here, we're going to look at the first two kind of basic SUVAT equations and where the ideas come from. So if I just quickly remind you of what the different letters stand for and what we've got going on. Time, T is representing the time passed. So the time interval we're dealing with in that question. So the time passed. And please do feel free to share what you recognize these symbols to mean. We're just going to hopefully clarify this. S represents the final displacement. So sort of how far it's kind of ended up away from where it started during that interval of time. So final displacement after time T. After time T, cool. From the point when T is 0. A is obviously acceleration, and I'm just going to make a note that this is constant acceleration. This is when the acceleration is a fixed value. So that's really key to when we use this idea. This tells us to use SUVAT. Brilliant. And some other ones people have added. Excellent. U is the initial velocity, the initial speed, initial velocity. So I would say at t equals 0. We can think of that at the time 0. And lovely. And then v is the final velocity. So that's great. And that's after the final amount of time. So brilliant. And great if you're familiar with that. Now we're going to look at where these first two SUVAT equations come from. So if we take this sort of generic graph representing the velocity time of an object, and you've got the equation of the graph. Now you might recognize from GCSE, this is like a y equals mx plus c graph. You might think in terms of pure maths, it's a straight line graph. There's some gradient and there's a y-intercept. If we connect this in with what we've just labeled as those different variables, y is v. The y-axis is what the velocity is doing. So calculating v is equal to, now remember we said that the gradient on here is the acceleration. So we can denote the m as a. The x-axis is the time axis. And the y-intercept, does anyone know what we're calling the y-intercept in this context? At the initial time of 0, the velocity that it's doing, what do we denote that as? What did we mention that the initial velocity was referred to as? Brilliant, well done, excellent to all of you. Yeah, absolutely, it's u. Now you may have learned that this, you might be kind of familiar with writing it this way around, v equals u plus at. But that shows us where this idea comes from. So for those of you that have seen the SUVAT equations before, you'll certainly recognize this one. This is often the one you start with. And it can kind of be derived from that concept of a y equals mx plus c graph. And the reason that this is SUVAT is because the acceleration is constant. It's a fixed value and it's got that fixed gradient. So hopefully that's brought to life kind of where that v equals u plus at comes from, directly from that graph. Excellent. So the area under that graph, we can think of, right, so it's sort of like a trapezium shape. Say I fix a point along that. Excellent. The area represents the displacement, which we're using what letter to denote? What letter do we use in SUVAT for the displacement? Because the area under here represents how far it's gone. So if the area is the displacement, we can think of that as equal to, brilliant, S, well done. So we can now start thinking about, can I form some equations that represent that area? And let's look at what we've actually got going on. How would I find that area sort of numerically? Well, it's a trapezium shape. If you think about it, this is parallel to this bit. You could obviously split it up into a triangle and rectangles and stuff. But if we think about that then, if I'm trying to get an expression for the area of a trapezium is half of the base, half the distance between the parallel lengths, which is effectively the base of this. So we might be used to calling it h and then times a plus b, which are the parallel lengths. Now that height is u, and that height is the final velocity at the time we're dealing with along here. So if we put that all together, what we'd get is S, the area, is equal to a half times the time elapsed times the initial velocity plus the final velocity. So you may have seen that written as S equals u plus v over 2 times t. Brilliant and well done. Thank you so much to all of those that have shared that in the chat. That's superb. And now putting it in light of these variables is really useful. So very well done. We're going to do some questions now, like we would see in an exam, and then obviously build on to the harder SUVAT equations as well that stem from this. So let me know if you recognize those first two kind of key SUVAT equations, because they can be derived straight from a generic graph. And then obviously we can kind of quote them and use them in the questions. So let's have a little look, but it'd be great to hear from you if this is very familiar. That's great. Let's work through a question together now. So solving a SUVAT problem, find the distance traveled by a car as it accelerates from a velocity of 5 meters per second to 20 meters per second over 8 seconds. So feel free, if you're kind of confident with this, to work ahead of me, get an answer and share it. That's excellent. Yeah, brilliant. Good. So the first thing we're probably going to do, if this is new to you, is list what we've got going on. List given and required quantities. So let's have a little think about what we know and what we need to know. Quantities, yeah, let's have a little look. So what we've got here is out of S, U, V, A, and T, what do I know? I've been told from a velocity of that to a velocity of that over that time, and I'm looking for the distance traveled. So what we want to do here is think about what have we got? So S, we're looking for. U, we know. Brilliant. Some people have worked ahead already. U equals 5, V equals 20, T equals 8. And then what we need to do is choose the correct SUVAT. So what one did people choose there? So choose the correct equation. So we've just said that S equals U plus V over 2 times the time, and then rearrange and sub in if necessary. But actually the subject of what we want. And then the substitute, sub in known values, and well done for those that have already done it. Let's have a little look. So S is equal, whoops, sorry guys, my pen went a bit funny there. S equals to U plus V, so 20 plus 5 divided by 2 times 8. And I agree with you all there. Absolutely, that will be 100 meters as the displacement. And very well done if you use the correct units there as well. Welcome to anyone that's just joined, and thank you so much to those sharing comments and answers as we've gone. That's been brilliant. Little quick checkpoint there for you then. If you could just let me know how you're feeling. 1, if this is really straightforward, as I know some of you have said, you're quite happy with this. 2, if it's kind of okay. And then 3, if I've super confused you, which hopefully isn't the case. Certainly not looking at the chat. It looks like we're all pretty confident with this. So that's lovely. Just to give me an indication, and obviously let me know how you're finding that. We're going to crack on though. That's great. Feel free to just give me a quick indication as we go. Lovely. Okay, so here's a really good question to look at with this stuff here. So this is like an exam style question for us to go through. Brilliant, great, lovely, overwhelming amount of ones. That's what we want to see. Excellent, great. A lift is traveling upwards and accelerating uniformly. So this is actually the indication that this is a SUVAT question. A is a fixed value. Okay, so it's accelerating uniformly. During a 5-second period, it travels 16 meters. The speed of the lift increases from U to 4.2. We want to find U. So the unknown is U, the initial velocity. Now, as I said, feel free to work ahead of me. I am going to whiz through this one now. So what do we know? We know that the time elapsed is 5 seconds. So it's a 5-second period. We know that S, the displacement, is 16. We also know that actually, do we know the initial or the final velocity here? What one do we know? What letter am I going to use to represent the velocity that I do know? So I've got the final, which is the letter V. So V is 4.2 and U is the one I'm looking for. Brilliant. So what we can think of is, obviously we said we've got this SUVAT equation that we know, and we kind of want to make U the subject, or plug the values in and then rearrange to get U on its own. Brilliant, and well done to those of you that have already kind of worked through that. So 16 is equal to U, which we don't know, plus 4.2 divided by 2 times by the time, which is 5. So I could times up by 2, 32 equals U plus 4.2 all multiplied by 5. So then I could divide by 5 and then subtract 4.2 to leave me with U, which hopefully, and just double check, is that 2.2? Do we agree with that? and that will be meters per second because it's a measure of velocity. Okay, excellent. Cool. Brilliant. So I'm going to carry on. I just want to do the next part, and I'm conscious of the time because obviously we want to get onto the harder SUVAT equations. So we're going to do the acceleration, and if any of you have already done this, please feel free to share and suggest what you got. So again, we know some more information now for part B. We also know U. So I know T equals 5. I now know that U equals to 2.2. I know that S is 16. I know actually everything else really, don't I? V equals 4.2. So if we use, yes, absolutely. So there's a great deal of different ways the questions can come up in SUVAT. It could be sort of simultaneous equations sometimes. Typically for these kind of questions, it's very methodical. There's one thing missing, you plug it in and you find the bit you haven't got. But these problems do get much harder. So that was a brilliant question there. Cool. So if I'm looking for this one, I'm going to use V equals U plus AT. And obviously for this one, I don't actually need S. So what I can do here is I can say that 4.2 equals to 2.2 plus the acceleration that I'm looking for times the time that's elapsed 5, rearrange and make A the subject. So minus 2.2 off and divide it by 5. So we're going to get A is equal to V minus U over T is the rearrangement. Some of you might have learned that as a separate SUVAT equation, but it essentially comes from this one being rearranged. So that's going to be 4.2 minus 2.2 divided by 5. And well done to those of you that have done this already. I'm just going to double check I got the same. So that's going to be 2 divided by 5. So 0.4, absolutely. And that will be meters per second squared. Lovely. Well done. Brilliant. So I'm going to keep going. And now we're going to look at some slightly trickier SUVAT equations. Oh, yeah, absolutely. Sorry. So some people have asked, could we have used a different SUVAT equation there? Yes. And that's what we're going on to now. And when you know all of them and eventually you're kind of finding all the values, you've got a little bit more at your disposal to use. And that's what we're building up. So these are the last sort of main SUVAT equations that we're going to look at and use. We're going to derive. So using the two we've already got, I'm going to show you where the other SUVAT equations come from. So what we can do here, combining this information, is if I know that V is equal to this, and I know that S is equal to this, I can kind of put that together in a couple of different ways. So S is equal to U plus V over 2 times T. But we've also learned that we can write V like this. So I could actually say, instead of U plus V, I could write U plus AT. Does everyone get how I've done that? So what I've basically done, yeah, excellent. What I've basically done here is replace the V equals U plus AT and taken the V and put that in place as U plus AT. So I've not got V in this equation anymore. And if I tidy this up, S equals to 2U plus AT, it's all getting times by T as well, isn't it? Over 2. And if I go a step further and tidy that up, S equals to, that would be 2UT plus AT squared over 2, which would come out as UT plus a half AT squared. So who recognizes that one? That's another kind of classic one. Anyone that's done a lot of mechanics, a lot of kinematics will know that that actually ends up being a kind of favorite of the questions. So who recognizes that? Hopefully that's a kind of standard one. And we're like, okay, yeah, I can see how that comes about now. So let me know if you recognize that. Brilliant. Well done. And actually, while we're looking at this, there's another very similar scenario that we can actually, so obviously we can stop there and say, there we go, we've derived another SUVAT equation. But again, if we think about it, if U plus AT is V, that means that U is equal to V minus AT. So if I sub that in as U, I'd actually get S equals to V minus AT times T plus a half AT squared. And that will actually come out as VT minus a half AT squared, which is like another one we learn for displacement that can kind of stem from that one. So that's great. That's brilliant to see. Well done. So then the other way of combining it is if we, this time, think about replacing t here. From the equation v equals u plus at, what I can actually do with that is I can make t the subject and say t is equal to v minus u over a. The difference in the velocities divided by the acceleration tells me the time that's elapsed. And if I plug that in as t into here, I'd get s equals u plus v over 2 multiplied by t, which is v minus u over a. And if we do this carefully now, because this looks a little bit more involved, let's have a little look. What we're going to get is s equals to, and I think people get a bit scared when we've got fractions all over the place and it's very heavily algebraic. But let's be careful with this. So on the top, we're going to have u plus v, v minus u, and on the denominator, we've got 2a. Didn't really need those brackets there, did I? And then if I tidy that up, you might notice that's a difference of 2 squares. Very good. Some people can kind of anticipate where this is going. We're going to get u squared minus v squared over 2a, and that's equal to s. No, we're going to do some exam questions of this in a second, absolutely. Yep. So if I times up by 2a, 2as equals to, oops, doesn't equal to that, equals to u squared minus v squared. So if I rearrange that, v squared equals to u squared minus 2as is probably the form you're likely to recognize it as. So this is a really good one to kind of how to derive them. Feel free to screenshot, make a note, add this to your notes if you don't kind of know how to get there yourself or didn't beforehand, because it's really good to be able to go through this process and be very confident and fluent with it. Lovely. So next one, we're going to actually do a question now using some of this stuff. This is quite an involved question. There's a few bits to it, so we need to sort of be careful. It's a really good one to go through. So again, if you're confident with this stuff, feel free to work ahead of me. We've got a 75 kilogram skydiver, initially falling at 80 meters per second, deploys their parachute, after which the skydiver experiences a constant 1,000 Newton resistive force. Calculate the time it takes the skydiver to fall 900 meters after deploying the parachute. Now, there's a few things going on here. And actually, I did mention at the start, one of the things we need to use is Newton's second law. Why might we need Newton's second law? What SUVAT variable value does that give us? How would that help? So SUVAT, what can we do here? So let's have a little think. The skydiver, the weight of the skydiver is 75 g, and that doesn't mean 75 grams. It's 75 kilograms, but I'm timesing the acceleration due to gravity. So that g denotes the 9.8 value. Brilliant. And the resistive force, when they're kind of falling with the parachute open, is 1,000 newtons. Superb. Well done to those that have mentioned that A is the value we're going to be able to ascertain from Newton's second law. Very good. So what we've got to be careful here with the force, it's very easy to think the force is the weight going downwards. It's the resultant force. So we've kind of got to resolve forces and think, or you might resolve in the direction they're going. It's actually the force is going to be the downwards force minus the resistive force. Okay. And for those of you that have done that, so if you do 75 times 9.8 and take away 1,000, you do actually get a negative number. So well done to those of you that are asking about this. If we're looking at it in a downward sense, this is where the direction comes into play. Why would I expect the acceleration to be negative? Bearing in mind, this is the point in the journey where the skydiver has deployed the parachute. So why would I expect now that the acceleration is negative? Because obviously the skydiver is still falling to the ground, but this is the bit people struggle with. So we need to really clarify this. Why would I expect it to be negative? It is decelerating. So although he's or she's fallen to the ground at very quickly, probably, the rate at which that's happening is getting less. So the skydiver's decelerating, but obviously still falling towards the ground. So minus 264.25 is the acceleration. And what is the resultant force. And I know the mass is 75. So if I want the acceleration, what I'm going to do here is A is the force divided by the mass. So that's the resultant force, which will mean that if I do that value, minus 264.25 divided by the mass, 75, I get an acceleration of minus 3.523 meters per second. Brilliant, well done. And it is decelerating. Cool, excellent. So that is the acceleration, which is negative, effectively meaning it's sort of going slower. The parachute would slow it down. And this is the kind of weird idea we're getting into. So what we've got now is we've got to start thinking about SUVAT. What have I got? I've got A, from Newton's second law, I've found the acceleration towards the ground now has become, whoops, it shouldn't be -1, it should be -2. I've also got U, which is equal to 80 downwards. So that can be kind of positive. So we're thinking about it in this direction. We've also got S. What is S? S is the displacement, and we want to calculate the time it takes them to fall 900 meters. So S is 900. And we've got to think, what am I actually trying to work out here? I'm trying to work out the time. So what SUVAT? Excellent, well done. The SUVAT equation I'm going to use here is S equals to UT plus a half AT squared. Okay, it's that one. So what we're going to do is we're going to sub in and solve a quadratic. And what is interesting about this is a quadratic could have potentially two answers, and we need to think about that and what that would mean. So we're going to sub in and solve quadratic, and we're going to do that now. So let's have a little look. So sub in that information into S equals UT plus half AT squared. Now you've got a calculator that solves it. For those of you that have a class WIRS or equivalent, it actually allows you to just type the quadratic in, or you could use formula, or you could look to factorize. Chances are with some of these mechanics questions, they're not going to factorize nicely. So we're going to be fairly reliant on the calculator for some of this. So 900 equals 80t plus a half times A, which was minus 3.523 times t squared. And I'd bring that all to one side, and I get a quadratic like 1.7616 blah 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 t squared minus 80t plus 900 equals 0. And now it's in that kind of user-friendly form for us to solve a quadratic. So you can kind of think of this as like the A coefficient of x squared or t squared, and then that's the constant, and you can kind of sub that into the quadratic formula. And please do let me know if you've got an answer, because this is where it kind of gets a little bit interesting and we need to be careful here. So what we get is we go t equals, and you could do that quadratic formula, or if you know how to use the calculator to solve quadratic just by typing it in, then obviously use that. And what we're going to get here is if we sub those values in, the answers that come out are t equals, brilliant, 20.5 seconds or 24.9 seconds. So which one is it? And this is weird because they're both positive, and it's like you can't hit the ground kind of twice. They can't hit the ground twice. So what one do we take? And also, why do we get another one? So this is interesting. What happens when they hit the ground? The motion all changes, they've landed. So actually what we do is we just take the first answer. That becomes redundant because once the ground is hit, the whole system goes out the window. They're not accelerating anymore, decelerating, they're on the ground. So because this is a quadratic, if you think about a quadratic graph, kind of like imagining that it goes down and then comes back up, goes through the ground and comes back up. We know that that motion stops once the ground has been reached. So although it's following this sort of parabola, that doesn't happen. You just take the first time. Is that clear? Does everyone get that? So we can just take the first value that comes out for the time there. And hopefully that's nice and clear. So what we'll do a few more exam style questions, but very well done for persevering through that. That was a good test of this content. So let's keep going. Just give me a quick indication again of how that was for you. A little bit harder than some of the ones we did before, but we're going to keep going with the exam questions now. So a quick indication of 1, 2, or 3. I'm going to keep going, but let me know. Okay. So here we go. A question, a lorry, excellent, fine. Please be honest, that's great. A lorry is moving along a straight horizontal road with constant acceleration. The lorry passes point A with speed u meters per second. U is less than 34. And 10 seconds later passes a point B with speed 34. So it kind of tells us it's increased. The acceleration should be positive because it's gone from something less than 34 to 34. Given that AB is 240, find the value of U. So again, feel free to work ahead of me with this. That would be great. Oops. So what we know is T is 10 seconds. So we've been given the time, we've been given this, we've been given this, and we're trying to find this. So T is 10, V is 34, whoops. U is what we're looking for, and S is 240. So let's use S equals U plus V over 2 times T. And you could obviously rearrange that if you want to as well. Let me know what you guys get if you're working ahead of me there. And we can rearrange that. We could do U equals 2S over T minus V if we rearrange that. Yeah, cool. And we're going to get 2 times 240 over 10 minus 34. Hopefully we got 14. Brilliant. Well done to those of you that worked through that. Very speedy there. That was good. Lovely. And then it says for part B, the time taken for the lorry to move from A to the midpoint of AB. This is where we need to be careful. So what we have to do here kind of carefully is we need to be, what have we got to look at? If it's the midpoint of AB, what is that actually telling us? So we now know U. So U is 14. We know T is what we're looking for. V we don't know, but S we do know. S is now going to be 120. And A we can work out. So let's firstly work out A. A is equal to, if we kind of think about finding A from what we already have, because we're going to actually need that first. We seem to be missing a few bits here. So if I firstly work out the acceleration, why can't I just half the final velocity? Because obviously the rate that's changing, the only thing I can half in this instance is S. So I'm going to need to do this in a couple of steps. So we'll do that now. So what have we got? If I think about finding the acceleration, because that will help me out, using the initial bit of the motion, T equals 10, V equals 34, S equals 240, and then I want to find A. What I can use is S equals VT minus half AT squared. Rearrange and make A the subject. And let me know if you guys get the acceleration ahead of me here. So the acceleration, well done for those that got that. You sub in, rearrange, make A the subject. A would be equal to 2 over 10 squared, I believe comes out as 2 meters per second squared. And now I can use that to find it for the midpoint. So now I'm going to just move this on. To find it to get to the midpoint of AB, I've got the initial velocity that I found was 14. S is now 120. I've just found that A is 2, and now I'm looking for T. So here I can use S equals UT plus a half AT t squared. And again, I'm going to get a quadratic. So for this one, I'm going to get 120, because it's the midpoint, it's halfway along to AB, equals 14t plus a half times 2 times t squared. If I make that kind of the way round I want it for a quadratic, all equal to 0, and solve, that actually does factorize, but you don't have to be factorizing that. You can use your calculator. And then obviously one of those values is negative and one is positive. This one is the one that works. T equals to 6 seconds. So this topic is AS kind of content, but it very much builds into year 13. And it's an idea that we use a lot, like loads in year 13 as well. So it's kind of a bit of an overlap, some of these harder questions. Brilliant. Cool. I'm going to keep going. So let's do this question quickly and see how we go. So it's another sort of fairly involved question. A crane is used to lift a load using a single vertical cable, which is attached to the load. The load accelerates uniformly from rest. What does that tell me? From rest. What do I know from that? When it has risen 0.9 meters, its speed is that 0.6 meters per second. Show that. So this is nice. At least they're telling us what the answer should be. Show that the acceleration is 0.2. So for this one, what do I know? Well, if it's from rest, well done to those that have already said that. That tells us u equals 0. Brilliant. We also know that v equals to 0.6. We know that s is equal to 0.9. And I'm trying to work out a, or show that a is 0.2. So the one I can use is v squared equals u squared plus 2as. And for that one, I can sub in carefully and obviously make the subject A, so I can kind of rearrange it. I'm just thinking, did I write that up properly earlier when we went through this? Yeah, sorry, that should have been plus when I rearranged it. Good. So here we go. Let's work this out. And as I said, feel free to work ahead of me and find A. Let me know in the chat if you found it. So A, we could rearrange that to v squared minus u squared over 2s. Subbing these values in, 0.6 squared minus 0 squared over 2 times 0.9 is going to give us what? What do we get? Superb, 0.2 meters per second squared. Brilliant. Now, the second part of this says, find the time taken for that to happen. So the only thing we haven't found is now t. So you've got kind of options for what SUVAT you could use. And we could just use the original ones we were given before we found A, but we know A is right because it was a show that question. So say, for example, we use the same things again, u equals 0, v equals 0.6, s equals 0.9, but this time I want t. I can use s equals u plus v over 2. Yeah, really good comments on this stuff. I'm not going to go through projectiles today, so that's sort of the year 13 extension of this, but obviously I'll talk about the Snap Revise free trial and the web classes we've done on that previously that you'll have access to, so that if you do want to look over material we've done on projectiles before, that is kind of available. But we're going to carry on with this idea and get this question answered. So if anyone's got the value of t, if you rearrange that, let me know what the time is. And you're absolutely right. If it's a show that, we can trust the answer is right, and we could have used A in this question, but we had options. So the answer for the time is, well done, is 3 seconds. Brilliant. Lovely. So we're going to keep going. We'll just do the final one of this, and then we'll wrap this up, and I'll just kind of answer any questions I can towards the end. So for part B, it says, given that the mass of the load is 800 kilograms, find the tension in the cable while the load is accelerating. So this is now what? Whose law are we using and which one? Big hint there. So this one is involving mass, acceleration, tension, forces. So this is Newton's second law for this bit. So remember, F equals ma, probably worth writing to go, okay, this is what I'm using. So F is the resultant force. Now remember, that would be if the thing's being pulled up like this, the tension in the cable, and the weight is kind of dragging it down, and it's accelerating that way, which we can denote with a double-headed arrow, 0.2, wasn't it? Yeah. So then the resultant force is the tension, which must be greater than the weight, because it's pulling it up, must equal to the mass times the acceleration. And then we can rearrange that, and we can get that T is equal to 800G plus 800 times 0.2. Well done, excellent. And that's going to come out as 160 plus 7,848 approximately. So it approximately what we're going to get there if we solve it is going to be 8,000. Oops, just cleared what I was writing there. Newtons. Okay, so using G as 9.8 again. Right, guys, I'm mindful of the time. I know I've gone through some of these difficult ones quite quickly. Very well done to those of you that got that. That's superb. And thank you so much to all of you today that have answered questions and shared comments in the chat. I'll try and do my best to answer any of those now as well. So we've done these key ideas. We've derived the SUVAT equations. We've used them, and we've used them in light of a kinematics problem, and also trying to develop sort of ways to sense check your answers as well. Another thing I say to a lot of students, including those doing projectiles questions and any of these mechanics questions, is most of the motion happens in only a couple of seconds. So that's another way you can sort of sense check your answer. Now, what I'm going to quickly just mention before people head off, thanks very much to everyone for working so well there. That was brilliant. It's kind of flown by this session. I'd like to just remind you that we have got a 2-week free trial, and it's going to expire this code on Tuesday at midnight. So if you're interested in signing up and just trying it out for 2 weeks, looking on Snap Revise, I'm going to quickly show you how to do that. But there's, as I said, loads of resources that are past web classes and drop-ins where we've done the whole A-level syllabus, and as well as obviously the tuition service we provide to kind of tailor the support to what you're learning in school at the moment. So what I'm going to do, if I stop sharing that there for a second, and I'm just going to share with you the website just so you know how to kind of get there and put this code in. So hopefully you can see that now appearing on your screen. So on the Snap Revise website, if you click on tutoring, you go onto there. This is what we kind of offer. So say it was the A-level maths you want to support with, join now, and that's where you can put this code in. What we have is as I said, loads of web classes we've previously done, web classes every week, 4 sessions a week. And in terms of a kind of comparison to general kind of tuition, there's obviously lots of resources available for maths, lots of brilliant materials you can practice yourself online. But in terms of the one-to-one support that's given, there's a great deal of it. And for the kind of monthly cost, you're getting a lot of tailored feedback and support and help with the topics you want help with quickly. So please do look at this, especially if you just want to try it for 2 weeks and see if it's for you and it works well. And obviously the sessions, the web classes will be very much like what we did today, go through a key idea and some exam practice. But we also have drop-ins where, as I said, you can kind of email in questions and things you want help with. And as I said, there's a kind of whole catalogue of previous classes. You can go back. On Monday, we typically do year 12 web class and drop-in, and year 13 and a drop-in after on Wednesday. So the dates are all there, the topics that will be covered, and also obviously the previous ones you can watch back and go over. So that might be something you'd be interested in, but certainly do the free trial and see if it's for you. It'd be great to see some of you on there as well, especially given how well and efficiently this session's worked. So that's been really lovely. It'd be great to see you in some of those sessions. What I'm going to do, I'll stop sharing that for a moment and reshare where I was at. So there, as I said, is the code that you can find by clicking join now on the tutoring part, typing the code in. That'll give you 2 weeks to try this out. That's lovely. Thank you for all your hard work there and the comments and keeping the chat moving nicely through these questions. That was really great, and some really good points. It'd be great to see you, as I said, at future sessions. So please check that out if you're interested. And let me just check. I think yeah, the only other thing is the Sunday sessions for each of the subjects. Do set a reminder on YouTube, and they're sort of each subject covered on a different Sunday. So have a little look at what's coming up, but also set reminders. And as I said, it'd be great. Hopefully we can support you in your other subjects as well, and see you in future sessions. Really well done. Thanks again for all your hard work, guys. That was lovely. I'm going to stop sharing that there. And yeah, as I said, it'd be great to hopefully see you soon. I hope you all keep well and keep persevering through what's been a kind of really extraordinary year, and keep on top of the work. But as I said, we're kind of here if you need any additional support. And yeah, it'd be great to see you then. Well done. Thank you very much again. And all the indications of how you found the difficulty in the pitch of what we've gone through. Very much a big A-level topic there. So it was great that we managed to get through all that content and kind of work efficiently. So that was brilliant. Well done. Lovely. Take care, everyone. And yeah, as I said, hopefully see you at a session soon. That'd be brilliant. Well done. Cool. Have a good week and keep well.